Hey folks, welcome to another set of Chemistry 2 video notes. Today we'll be covering Chapter 5, which is all about chemical bonding and nomenclature. I'm going to try to cover all of these book sections here, but if any of these get too confusing, or you'd like a slightly different explanation of the same concepts, I strongly recommend reading this chapter. Let's get going. First up is ionic bonds. As you may remember from previous chapters, we know that metals tend to lose electrons, becoming positively charged ions or cations, and nonmetals tend to gain electrons, becoming negatively charged ions or anions. In fact, usually the electrons that the metal loses will be completely transferred to the nonmetal. The magnetic-like attraction between positive and negative ions is called the electrostatic force. The strength of that force is governed by Coulomb's law, which is F equals K times Q1 times Q2, all divided by r squared, where F is the attractive force, K is a constant that you can largely ignore for now, Q1 and Q2 are the charges of the particles, and r is the distance between the nucleus of the particles, or the internuclear distance. The larger your charges are, the stronger the forces of attraction will be. The closer your particles are together, the stronger the forces will be as well. If your charges are both positive or both negative, you'll end up with a positive attractive force, which represents repulsion. If one of your charges is positive and the other one's negative, you'll end up with a negative force, which represents an attraction. This attraction between charged particles is what we call an ionic bond. An ionic compound is not usually made up of just two ions, but a whole mess of ions that arrange themselves in an orderly fashion so as to maximize the amount of attraction between each particle. Take sodium chloride, for example. This particle diagram doesn't show just one Na and one Cl, but a bunch of NAs and a bunch of Cls. They're arranged in a specific three-dimensional way that puts oppositely charged particles as close together as possible, while putting the same charged particles further apart. This maximizes the attractive forces and minimizes the repulsive forces. We call this orderly 3D arrangement a lattice structure. A crystal lattice is one that's highly ordered, like that of NaCl. An amorphous lattice, on the other hand, has no overall order to it. Because ionic bonding is so strong and these lattices are so highly ordered, it takes a lot of energy to cause crystalline solids to melt. The amount of energy it takes to pull ions out of this lattice or to break the lattice structure apart is called the lattice energy. The stronger the attractive forces, the higher the lattice energy. Generally, crystalline lattice structures are hard to break without using some kind of impact force. Salt is not so easy to break by squeezing it between your fingers, but if you hit it with a hammer, it'll shatter. This is due to the highly ordered arrangement of ions. When you hit the structure, the impact will cause some ions to shift, butting up next to their similarly charged counterparts and increasing the repulsive forces. This pushes the layers away from each other in an action that we call cleaving. Molecules are unlike compounds. In molecules, there are not lattice structures with seemingly unknowable amounts of particles stuck together. There are distinct individual molecules made up of a handful of nonmetallic atoms bound together in a specific way. Each molecule will have the same number and type of atoms within it. The properties of a molecule are not an average of the properties of each element it's made of. We have to know about the types of bonds within the molecule and the shape that the molecule takes in order to even somewhat predict its properties. There are two types of molecules: molecular compounds and elemental substances. Molecular compounds consist of at least two different types of elements, whereas elemental substances may have more than one atom, but all of those atoms are of the same element. So, if electrostatic forces of attraction hold ions together in an ionic compound, what holds atoms together in a molecular substance? If you guessed covalent bonds, you're exactly right. A covalent bond is formed by the attraction between the electrons of one atom and the positively charged nucleus of another. When this occurs, the electrons are considered shared, as they exist largely between the two nuclei, and both atoms can claim them, so to speak. In this case, the electrons don't get transferred from one atom to the other, they're just shared between them. The only electrons that participate in covalent bonds are valence electrons. That's where the name covalent comes from. Core electrons, or those that are not in the outer shell of the atom, are too close to their own nucleus to want to be shared with another nucleus. We can represent covalent bonds in a few different ways. We can put a pair of dots between the two atoms, or we can replace those dots with a line. Another way we can represent this type of bond is to draw the two atoms out with the shared electrons between the two nuclei. Here are some images that may help you see this a little bit better. In each atom, the electrons are strongly attracted to their own nucleus. As the atoms become closer together, they can start to form some attractions from the electrons of one atom to the nucleus of another. They'll continue to come closer together until those attractions are maximized and everybody's happy. If you push those atoms any closer, the repulsion between the two nuclei will become too much to handle, and they'll push back apart. Once the attractive forces are maximized and the repulsive forces are minimized, the set of atoms finds itself at its lowest potential energy. That's represented on this graph here. The y-axis is the potential energy, and the x-axis represents the distance between the nuclei of each atom. You can see that there's a certain point on this potential energy graph in which the two atoms have the lowest amount of potential energy. At that point, the location on the x-axis represents the length of that bond. One important thing to note about covalent bonds is that we release energy when these bonds are formed. In order to break these bonds, we have to add energy into the system. This is always the case no matter what. It's also important to note that we often represent these as having these shared electrons strictly between the two nuclei, which is accurate for the most part, but occasionally the electrons will move around and exist more on one side of the atom or on the other. This will become important later. So cool, now we know about these two types of bonds, but the real question is, why do atoms bond together at all? Well, the answer to that question, my friend, is the octet rule. Atoms will gain, lose, or share electrons so that they can have 8 valence electrons. You've already seen this with ionic bonds in the last chapter, so we'll just focus on the covalent bonds for now. In order to predict how the covalent bonds will form, look at how many valence electrons each atom has, which can be determined by its group on the periodic table. Figure out how many more electrons that atom needs to have 8 in total, and that's the number of bonds that atom is willing to form. For example, carbon has 4 valence electrons. It needs 4 more electrons to get to 8, therefore it's willing to form 4 bonds. A nice pictorial way to represent this is by drawing the Lewis dot diagram for each atom. This includes both the element symbol and some dots representing the atom's valence electrons. The electrons like to spread out as much as possible, so place them on the 4 sides around the symbol, and then pair them up as you run out of room. The unpaired electrons are the ones that are most likely to participate in covalent bonding. If you take the Lewis symbols of 2 elements and put them close together in a way that the unpaired electrons of one atom will pair up with those of another, you'll have officially drawn a Lewis dot diagram. When you do this, be sure to double check your diagram and see that each atom now has 8 electrons around it. When 2 atoms share more than one pair of electrons between them, you get multiple bonds. Predictably, a single bond has a single pair of electrons, double bond has 2 pairs, and triple bonds have 3. There are 4 simple steps to drawing these Lewis dot structures for molecules, which need to be followed especially if you have more than just 2 atoms bonding together. First, figure out how many total valence electrons you have. Next, place the least electronegative atom in the middle, and then connect the remaining atoms to it using single bonds. Hydrogen will never be the central atom. Remember, each of those bonds represents 2 electrons, so subtract those from your total, and then place the remaining electrons around the outer atoms first. Once you've placed all your electrons, evaluate your structure and see if all atoms have an octet. If not, move some of your lone electrons or lone pairs so that they become bonding pairs. Sometimes you can have more than one valid dot structure for a molecule. Each of these structures is considered to be correct, though some are much more preferred than others. As long as you've fulfilled all octets, your structure should be good to go in most cases. If you have multiple structures that are equally favorable, they're considered resonance structures and are often shown together with arrows between them. The actual molecule is a combination of all these resonance structures. Polyatomic ions are like molecules, but they have a charge. You deal with these in the same way as you do a regular molecule, but when determining the total number of valence electrons, you need to subtract 1 for each positive charge or add 1 for each negative charge. You might recall that electronegativity is how well an atom can pull shared electrons toward it. The higher the electronegativity, the more the atom can pull those electrons in. If two atoms are covalently bonded and they have the same electronegativity, the electrons are considered to be shared equally between the two atoms, and you have a nonpolar or pure covalent bond. If there is a difference in the electronegativity values, the electrons are shared closer to one atom than the other, and we consider it to be a polar covalent bond. Since the electrons hang out more on the electronegative atom, that atom is considered to be partially negative. The other atom would then be partially positive. This is where we get the name polar, like the two poles of a magnet. One end is positive and the other one's negative. This is most nicely represented with an illustration of electrostatic potential. The larger, more blue end is the side that has the electrons hanging out more often, and that's the more electronegative atom. We can also talk about the bond character. Bonds are either nonpolar covalent, polar covalent, or ionic in character. The larger the difference in electronegativity, the more polar or ionic the bond becomes. This is represented nicely on this image here. Remember, the ionic bonds only occur between metals and nonmetals, and they involve a complete transfer of electrons. That's why there's hardly any electrostatic potential shown on this image between those two atoms on the right. We can also represent the character as what percentage of that bond is ionic, which we can base off this graph here. Take a moment to analyze the table to the right and see if you notice any interesting patterns. Okay, we're almost done, I promise. Naming chemical compounds is one of those things that's super duper easy if you follow the steps outlined for you. The two easiest types of compounds to name are binary ionic compounds and binary covalent compounds. For ionic compounds, you write the name of the cation, or the metal, first, just as it is as an element. Then you write the nonmetal, or anion, next, with an "-ide" ending. Here are some examples so you can see how that "-ide" ending is applied. To find the formula from a name, you have to write down the symbols with their charges first, then add subscripts for each element so that you have a total overall charge of 0. Again, you can see this in the examples here. Most transition elements are able to form multiple positive ions, so we have to specify which ion we're talking about by writing a Roman numeral next to the name of that ion. For covalent compounds, you follow much of the same procedure, but these atoms do not form ions, so there's no way to predict how many of each atom will be in a molecule. Due to that, we have to use prefixes to indicate how many of each type of atom there is. The Greek prefixes that we use are listed here for you. The first element we write down is usually the least electronegative element. We treat it just as we would the metal in an ionic compound, but if there's more than one of those atoms in the molecule, we have to use the prefix. The second element would get treated like the nonmetal in an ionic compound, as we place the "-ide" ending on it, but we have to use a prefix regardless of how many atoms of that element are in the molecule. Ternary ionic compounds consist of an element and a polyatomic ion. Here's a list of the common polyatomic ions. A nice trick for remembering the ions with a nonmetal and an oxygen is that in order from least to most oxygens, they're named hypo, ide, ate, and per, which is short for hyper. For example, ClO is hypochlorite, while adding an oxygen gives us chlorite. Adding another oxygen gives us chlorate, and then another is perchlorate. Other than that, just look at what other elements are present. Chromate has 1 chromium, but dichromate has 2 chromiums. The only positive polyatomic ion is ammonium. Even though ammonium doesn't have any metals within it, it can act as the cation in an ionic compound because it has an overall positive charge. These are named in the same way that we name binary ionic compounds, but we don't change any of the endings on the polyatomic ion names. We write them just as they are. To go from the name to the formula, you do the same exact thing as you would a binary ionic compound, but if you have to add a subscript to indicate that there are multiples of a polyatomic ion, you must place the polyatomic ion in parentheses with the subscript on the outside of the parentheses. Lastly, in our section about naming, let's talk about acids. As of now, you can assume that any substance that breaks apart in water to create an H+ ion is an acid. We only name these acids using these special rules when they're dissolved in water. As a compound by itself, we'll name the acid just as we would under normal naming rules. If your formula is hydrogen and some other nonmetal or oxygenless polyatomic ion, you simply name the non-hydrogen part of the formula, with hydro at the beginning and ic acid at the end. So when hydrogen fluoride is placed in water, it becomes hydrofluoric acid. If your acid contains a polyatomic ion with oxygen in it, it could have one of two names depending on the ending of your polyatomic ion. This is similar to before, but the ending will either be us or ic acid, and we drop the hydro beginning. If your original name ends in ite, like sulfite, it will be an us acid, like sulfurous acid. If it ends in an ate, like sulfate, it'll be an ic acid, like sulfuric acid. All right, 2 quick things to wrap this all up. As always, there are exceptions to our rules. Some atoms are happy with more or less than a full octet. Electron-deficient atoms have less than a full octet and may include hydrogen, which follows the duet rule, beryllium, which is happy with 4 electrons, and boron, which is happy with 6 electrons. Atoms that have more than 8 electrons have an expanded octet. These may include any element in period 3 or beyond. Remember, each energy level can hold 2 n² electrons. So period 2 atoms can only ever have 8 valence electrons, which is why they do not form any expanded octets. Atoms in period 3 may hold up to 18 electrons in their 3rd energy level, so they may form expanded octets. The last thing I'll mention is formal charges, which are new to you, but extremely easy once you get to practice with them. Formal charges are just a bookkeeping system to help us recognize which atoms are happy with the way the electrons are arranged around them. They do not represent any actual charges. If you're able to draw more than one Lewis structure for a molecule, you can usually decide the most favorable one by looking at which one has all of its atoms with full octets. Sometimes that's not the case, and you have to assign formal charges to see why one is more favorable than the other. To assign formal charges, you look at how many valence electrons an atom would originally have, subtract 2 for each lone pair of electrons around that atom, and then subtract 1 for each bond attached to that atom. The total of all your formal charges should add up to the 0 for molecules, or to the overall charge of your polyatomic ion. Usually the structure which has the lowest formal charges on your atoms, which is often 0, will be the most favored structure. Otherwise, if there has to be a negative formal charge, you want it to land on the more electronegative elements. Look at this example of sulfate here. This is a polyatomic ion with a 2 negative charge, so all of our formal charges have to add up to 2 negative. The first Lewis structure puts all atoms with a full octet. If we were to assign formal charges, each oxygen would have a formal charge of -1, and the sulfur has a formal charge of +2. The more preferred structure, though, has an expanded octet for sulfur, so that 2 of the oxygens and sulfur have formal charges of 0, while the other 2 oxygens still have their formal charge of -1. Because the formal charges are lower on the second structure, this is the more favored structure. Well, that's all for today, folks. We will spend plenty of time practicing these concepts, so if you start out a little bit confused, that's okay. There are 2 easy ways to fix your confusion. Read your book, or as always, ask me questions.